Assalamu alaikum. So we are discussing the first chapter from the theory of machinery and mechanism. So today's topic is about the mechanical advantage for the mechanism. So yesterday, in our last lecture, we did discuss about one of the example and Grashoff's law. So the Grashoff's law helps you to evaluate if the mechanism is able to perform any useful work. So it was very simple evaluation you can use with the Grashoff law to find out if the mechanism is doing any useful work, and by using one of this equation. This, what is it basically? So the sum of small and large link, the smallest and large link must be equal to less than the sum of other two links basically. So we got one of the next topic is mechanical advantage. So in general, the mechanical advantage of the mechanism is defined as the ratio of the force or torque exerted by the driven link to the necessary force or torque required at the driver. So basically the input and output comparison is a fundamental definition what we follow for the mechanical advantage. So with the widespread use of 4-bar linkage, a few remarks are in order here that will help to judge the quality of such linkage or its intended application. So because most of the calculations we have done during this lecture is about 4-bar linkage, and in continuation of that 4-bar linkage we are also doing the mechanical advantage calculations for the 4-bar linkage as well. So consider the crank rocker 4-bar linkage as shown. This is figure 1.31, where link 2 is the driver. So this is the driver, and link 4 is the follower. So basically this is driver, this is driven link basically. And you can just think about it. So this is like link 1 is a fixed, link 2 is a driver, link 3 is a connection coupler basically, the word we have been using. So which is BC link, and then you got a CD link which is the follower, and there are a particular angle at some particular posture. So at this particular position, the angle which is being made by link AB, which is the driver, and with the coupler is the beta, and when it says link CD and it's making an angle gamma with the follower basically. And we will discuss the other positions as well. So these are the main elements and the respective angles basically. Yeah, so this is like same figure. So here the mechanical advantage is basically the radius of CD. So that's the CD, the follower. Why we are calling as a radius or as a length? Because it has to make complete revolution. So that's why it's been called as a RCD. And its angle sine gamma with this one, with the follower. So this angle and this radius is on the top, and in the bottom we got RBA. So this one, RBA, which is this length, and sine of beta basically. So this mechanical advantage we will certainly discuss in detail in coming lectures, but this is for 4-bar linkage. This is very simple formulation. So what you need, is just the length of the follower, and length RAB is the length of the driver where you're doing the input, and the sine of angles what they are making with the follower. So for example, RCD is making gamma angle and RBA is making beta angle over here basically. So note that this is directly proportional to the sine of angles gamma. So we got this one, mechanical advantage, is directly proportional to sine gamma between the coupler and the follower, and it is inversely proportional to the sine of angle beta. So inversely proportional to sine of beta. If I write it, MA mechanical advantage is directly proportional to sine of gamma, and mechanical advantage is inversely proportional to sine of gamma, sine of beta basically. That's what we are explaining here. Between the coupler and the driver. Of course, both these angles and therefore the mechanical advantage are continuously changing as link moves. This is interesting thing here. So you can imagine when it's moving, then of course the angle beta and angle gamma both will change continuously. So what does this mean? The mechanical advantage is a variation, or is a variable basically, and how it's changing? By the sine of gamma with this angle with the directly proportional, and sine of beta as this angle basically. Right. So when the sine of angle beta becomes 0, so you just imagine the sine of beta, this whole component becomes 0. So the mechanical advantage would be infinite. That's what we are saying. When the sine of angle beta becomes 0, the mechanical advantage becomes infinite. Again, so within this equation, if sine beta becomes 0 for any particular value of beta where the sine beta is 0, so the mechanical advantage would be maximum basically, or infinite. So thus at such posture only a small, so now we are explaining what is meant by infinite mechanical advantage. So at such a posture only a small input torque is necessary to produce a very large output torque load. So if the mechanical advantage is really maximum for any component, you do a little bit of work and it will do very large output torque or load basically. So this is the case when driver AB is directly in line with the coupler. So when this line actually is explaining the beta angle. So what it says, this is the case when the driver, this AB, is directly in line with the coupler. So this one and this one is line. So basically beta is 180 with BC as shown in figure 1.31. So now you got this. This is the line where so when the crank is in posture AB1, so you got AB1. So you got this is A, this is B1, and of course the coupler is then a straight line. So now you just think about it, this is the value beta. So AB1 is the driver, and then you got this beta, which is basically 180 degree. So if you plug in 180 degree for sine of beta 0 or 180, what does this mean? It means you got a 0 value of sine beta. So when the crank is posture, it occurs when the crank is in posture AB1, and again when the crank is posture AB4. So this is one case, and the other case is when AB4 is the case basically. So now Again, you got a coupler. This is the coupler, the three link three, and this is AB is a crank. So now we got basically so there are two lines here. So one line showing the coupler and other line showing the crank. So basically you got angle 0. So beta becomes 0 over here. So these are the two postures where you got one beta 0 and in other case beta 180. So in both cases the sine beta will be 0 basically. So if you take sine of both. So note that these also define the extreme posture. So these are the extreme posture as well. So when this is here, so that's the extreme point where this link can go. And this is the B1, this is the extreme point where the link can go of the travel of the rocker DC1 and DC4. So respectively, if this is the extreme, so DC4, this is also the extreme point, and this is also the extreme point for this DC basically. So when the four-bar linkage is in either of these postures, the mechanical advantage is infinite. That is, when beta is 0 or beta is 180 and the linkage is said to be in a toggle posture basically. So toggle means it is on its extreme limits now. If it's on either on this position or if it's either on this position. So in any case, it is basically in the toggle posture, basically on the limits. And mechanical advantage, by using this formula, uh, we will have the infinite mechanical advantage. In next coming lectures, in next chapters, basically, we will see how this mechanical advantage is being determined. But this is the way it is. It's more like explaining the fundamental of mechanical advantage for four-bar linkage. Right, so the angle gamma, so now we are explaining the angle gamma. So the angle gamma between the coupler and the follower is called transmission angle. So this particular angle is called as a transmission angle. As this angle becomes smaller, the mechanical advantage decreases, and even a small amount of friction might cause the mechanism to lock or jam. So you can just think about it, because mechanical advantage is directly proportional to sine of gamma. So as this angle becomes smaller and smaller, so smaller and smaller means we are again approaching, like we are approaching 0, for example. So in that case, you got this mechanical advantage to be really reducing. So mechanical advantage is reducing because both are directly proportional. So what does really small value mean here basically? So if you got sine gamma really small, even a friction which is normally a very little effect in four-bar mechanism, so frictional loss is really low. So what is saying, even a small amount of friction might cause the mechanism to lock or jam. So it will not move, because mechanical advantage 0 means it's not doing anything. It's more like a structure basically. So if somehow this value approaches 0, means mechanical advantage approaching 0. So at that particular value of gamma, where the mechanical advantage approaching 0, it will behave as such if you apply a little bit of the friction, or friction is basically itself. So friction will cause the mechanism to lock or jam. So you will not have any useful work, which is the definition for mechanical advantage. So a common rule of thumb is that a four-bar linkage should not be used to overcome a load in a region where the transmission angle is less than, say, 45 or 50. So the fundamental work which we are carrying from the four-bar linkage, we try to get the work done during the process where the angle is greater than this value. This is an important point. As we have said in previous slide, this gamma is continuously changing. Of course, this changing means it has to go 0, it has to go 180, it has to go 90, so it has to do everything. But at some certain positions, its mechanical advantage, because of this sign of gamma, is almost nothing. So let's say you are doing some work with this mechanism. We try to avoid taking up any work done during the process where the gamma is less than 45 or 50 degrees. So this is rule of thumb. So if you take any work or anything to do, overcome the load during this angle, overcome the load in the region where the transmission angle is less than 45 or 50 degree, there is a chance that it will become a lock or jam. So it will become a structure. So once again, we try to avoid. So when you want to take some useful work from this component, basically. So what does it mean? It means it will continuously run, but you are taking a intermittent work output. We try not to take any work during the angle when it's less than 45 or 50 degrees. So this is rule of thumb. So the extreme value of the transmission angle occur when the crank AB lies along the line of the frame AD, basically. So the transmission angle is minimal. Yeah. So this actually continue explaining the such thing. So basically, what it says, the extreme value of transmission angle occur when crank AB lies along the line frame. So when this AB is in the line with the frame, so this is the extreme value of transmission angle. So in that case, you got like the gamma value as such, where you have the maximum value. So then the minimal is explained as well. It's also minimal when you got the straight line as well. Basically, it is fine. So if you want to read it further, so the further graphs paragraphs actually explains this phenomena. So now we are just solving one of the problem, which is example 1.7. All right, so one of the example. So it is asked to determine the mechanical advantage of 4-bar linkage in the posture shown in figure 1.32. So we got the initial angles. So this is the angle 60 degree, and that's it. So just one angle is given, and then the lengths are given. So RDA. So this is RDA. So this length. The frame, basically this is the frame where you got like the fixed, which is 180 millimeter. RBA is 60 millimeter, so that's the 60 millimeter RBA. So this is the input we are giving. So this is the driver basically. So this link AB link is 60 mm, and RCB is 210. So that's the longest link. RCB is 210 millimeter, and RCD, so this one, the follower, which is 120. So this is the follower, this is 120, and you got, this is the driver, this is 60, and you got this value, which is the coupler basically. So RCBA, this is 210. So these are different lengths are given. So of course this one angle given, so we need to work out the other angles actually. So that would be, then we can use the formula which we have discussed, the mechanical advantage, which is this one. So we can use this formula. So you can imagine we know the lengths RCD, RBA. Just we need to know the angles. So you don't know gamma, but you know beta basically. So that's what he's saying. The beta angle is 60 degree because you know the beta angle was basically the angle between the driver and the coupler. So that's what we have. All right. So now, so angle gamma and beta for equation 1.8. Sorry. So angle, this one angle is 60. We need angle between these two lines basically. So this is the crank and the coupler, which is beta basically, are shown in figure 1.3 and can be obtained from trigonometry. So we need to do some trigonometric function evaluation to find out these angles. So this is the angle beta, this is the angle gamma. So these two are the angles which we are interested in. So of course, it requires some evaluation of intermediate angles so that we can use the triangular method to find out the gamma. Yeah, and the link names are also for convenience are mentioned. So this is link 2, this is link 3, and this is link 4 basically. All right, so now step one by one. So first we want to find out the gamma. So just remember, so these calculations are based on when the angle is basically 60 degree at that particular position. So we will work out what is this parameter basically. So first of all, we need to work out. So he's solving one of this triangle, to find out at this particular position this length r dB. So from here to here, this length we are interested in finding, because you see this is one of the triangle. You got a 90 degree here, but doesn't matter. And you got this length, RAD as well. This length is known, and this length is unknown, and this angle is unknown basically. So you can use one of the law of cosines. So I have, for your convenience, I have added this from open source. So basically, if the a square, so a square is this length, is equal to b square. So you add this length and this length, b square plus c square, minus 2bc. So minus 2bc, 2 times these two lengths, and cos of angle between them. So this is the cos of this angle. So this is the way different components are linked. So if you want to find out this length, so this is the scale of this one, and then minus 2bc, 2 times product of these two and intermediate angle. So that's exactly happening here. So we got this 60, which is basically the link 2. This is this side, and 180, which is link this one, or AD. So this is AD, and so this side and this side minus product of both and the angle between both. So that's the 60 degree. So you can work out this RDB would be this one, which is now 158.74. Yeah, so you don't need to write so many. So 158.7 should be all right. 158.8 basically W5. So you got this length now. Now, if you use another triangle, so so you got now this triangle. So because you know this length, you are interested in finding this angle. So you got this triangle now. where you got the length of 3 is already given, length 4 is already given, this length you have worked out, and so on. So you can use, so you use same law of cosine. So this is being written in a little bit different way. So it's been rearranged basically. So what you are doing, if I write in form of numbers, so so you got if let's say this is fifth link, for example, I'm just making up this number. So 5 square, for example, is equal to 3 square plus 4 square minus 2 times 3 link 4 and cosine of gamma. So now you just rearrange this equation and you will find out these values. So just don't confuse. So this is the link number actually I have written. So link 5 is the number, link 3 is this link 3, link 4 is basically this number, this link, and so on. So this is the way you determine this gamma angle, right? So now we have the angle 60. You got the angle, you got the angle gamma basically. One thing is still missing. We need beta angle. That is the required basically, because we got to have mechanical advantage value of gamma, and we also need to have value of beta as well. So continuing that, so now again using same triangle, you can work out the angle gamma, sorry, this phi. How you can calculate? Because you know the length of this one, you know length of this one, you know angle. So if these three things are known, you can use one of the law of cosine, because you know within the one equation you got 3 lengths and 1 angle. So if you know 3 lengths, you can work out what's the 1 angle. So this is again the equation being rearranged. As such, you can determine the value of phi. So you can independently work out the angle of phi by using the lengths. So this is 158 is this length, 210 is basically link 3, link BC basically, and 120 is link 4, and then product of both basically just taking the cos inverse. Yeah, just be careful, some values has square as well, so you got like square, so just use correctly. All right, so now yeah, so once we have this phi value, if I can use somehow analyze this triangle, I can find out the sum of these two angles, right? I can find out the sum of these two angles, and because I know all the lengths, I got this length, I got this length, I got this length, and I got this angle as well. So but we don't need this at the minute, so we can use this angle and this length to find out what should be the angle. So that's what it's doing. So we got similar cosine law again. So 180 is basically this length, 60 is basically this length, length 2, and then we got one of this length, so this is third length here. So you see one of these cosine law, because we need 3 sides, so these are 3 sides, and then the product of these two, so the product of these two will give us the angle between them. So you know, when you have product of the two components, the angle between them you can find out basically. So here he is finding the total angle, which is beta plus phi is 100.90 degree. So you can work out. So then it's very simple. You, because you know beta plus phi, which is 100, and you already calculated phi by evaluating another triangle, and you can like use these two equations to find out what will be the phi basically, what would be the beta angle, because you know phi. That what it's doing. So you got beta, so sum of both beta plus phi minus phi. So phi is being calculated 34.57. So you can work out what's the beta value. So now beta is determined, gamma is determined, the work is done. So you can just find out what's the basically mechanical advantage. So mechanical advantage is this length and we use these lengths. So these two lengths we use, and here the sine gamma. So basically on top in this ratio we got RCD. So this parameter, this length, which is 120 millimeter, and whatever angle is being made with the follower. So that's 48. So basically 48 was gamma here. So this is the 48 angle which was being made with the follower, with the coupler, sorry. So this is the follower and the coupler is making angle of 48.65. So that's this angle. And then mechanical, so you got in the bottom, you got 60, which is this length, and the angle beta basically. So that's what we have determined. And we got the mechanical advantage of 1.64. Yeah. So normally in mechanical components, mechanical advantage of greater than 1 is the requirement. So you can have higher and higher value of mechanical advantage, but any useful machine will produce any mechanical advantage of 1.64. Once again, because when it's moving, for example, this one is so when it's moving, of course all angles are keep changing. So what does this mean? Mechanical advantage is not a fixed number. So it will keep changing from minimum to maximum. So you got some variation of mechanical advantage within the working of this machine, basically this mechanism. So considering this aspect, we just get the useful work done when the mechanical advantage is higher. So for any those positions where the mechanical advantage is less, we don't take any useful work. I will just explain this with the phenomena here with the quick return mechanism, which we have studied already. So in the quick return mechanism, we have discussed there is one working stroke and one is return stroke. So working stroke is a position where this work is need to be done, and during the working stroke this piston is actually doing some work by pushing this force basically. So there is a force in this direction, so this piston is causing this direction force in the reaction. So this is the point where actually we are getting a useful work. When it's going back this direction, the return stroke, we are not taking any work output. So that's why same way 4-bar linkage is required to do work when we have mechanical advantage highest during that phase. So this particular example, so mechanical advantage or the component will be designed in such way it has to do the functionality when it's in working stroke and we have the highest mechanical advantage. So I hope you understand the concept now. So we got mechanical advantage changing throughout the movement, but we try to use mechanical advantage for the phase where you got the movement being done in such way where you have highest mechanical advantage. And rule of thumb is we try not to do anywhere. A common rule of thumb is that a 4-bar linkage should not be used to overcome a load in a region where the transmission angle, so this particular angle, is less than 45 or 50. So you can see that this angle has to change from 0 to maximum 180, let's say it can go. So we try not to do any useful work from this, or we want not to get any useful work during the phase when we got 45 to 50 degree less than this range of angle. So if the transmission angle is less than this range, we don't get the useful work done, right? So that's the end of the chapter and end of this lecture set of lectures 2, slide 2. Um, we have covered most of the things here, uh, so we will continue with the next chapters.